So in today's video, we're going to introduce what a second derivative and how it's related to concavity, and I will also define what concavity means. So let's recap first derivative, or f prime. So here we have an interval chart where we have something to the left of a and something to the right of a. And we know that the slope here given is positive and negative. So what that means is anything to the left of a, the graph or the slope is positive, meaning the graph is going to go up. Anything to the right of a, the graph is going to go down. Now the question is, what could this function look like? So now it's a good time to pause and try to graph as many functions where you think that your graph can satisfy this condition here. So here we have two graphs to the left where the slope is positive to the left and going down to the right. So it follows the same pattern as this. And so these are the two popular ones. But however, these two graphs are continuous. There's no gaps at A. Now keep in mind, I did not give you any information about what happens at A. There could be a point there or there could be a gap. So ideally you should be able to open to different types of graphs. So here, the next one, we're going to graph one possibility. So I'm going to just take this left graph here and just split it up. So one possibility is this. So I think we did this before. We've seen this feature before, a jump. So we still have, it goes up and then it goes down, but at A, there is a jump. Or we can take this one here and just sort of split the parabola in half. Maybe this is going to be like this, and or maybe something like this. So the behavior is still the same. It goes up and then it goes down, but what happens at A, we don't know. Another possibility is, instead of having a jump, we can have something called infinite discontinuity, meaning we can have a vertical asymptote. So over here, I can take my graph and I can sort of go up, but I'm curving up where I'm going to create a asymptotic behavior. And to the right of A, I'm going to go down. Something like this. So something like a rational type of function, maybe a vertical asymptote. So these are just a couple of examples where there's many possible solutions or graphs to a given situation. So the message of this slide is, just because something goes up and down, it doesn't necessarily mean there has to be a turning point, because we've talked a lot about turning points in the previous video about first derivatives. So let's talk a bit about higher derivatives. So we've talked about first derivatives over here. So here is f prime, here's the first principles. And we know that if f prime is positive here, we know that the y values are going to go up, meaning the graph is going to go up, could be going up constantly, or could be curving up. It could be sort of like a square root feature, or maybe it could be like a combination of all these three possibilities. Now, if the slope is negative, so the y values are going down. So how it goes down, it could be straight down, it could be curving down, maybe not this part here, maybe scooping up, down, regardless, or maybe a variation of these, or maybe not that part. But the idea is the y values are always going down. How they go down, it really depends. It could go down constant, or it can go down getting more and more and more, or it could go down getting less and less and less. So now let's talk a bit about second derivative. Hopefully you've actually did the Desmos activity in regards to what second derivative means. But here goes. So if the first derivative tells you something about the y values, what the second derivative is, it tells you something about the slope. So when the second derivative is positive, that means something is going to increase. Well, what is increasing? Well, it's not the y value, it's the first derivative. So the second derivative tells you something about the first derivative, or in other words, the slope. So if the second derivative is positive, that means the slope is going to increase. Now the question is, what does the graph look like when the slope is increasing? Well, a popular one would be exponential. So we start off flat where the base is greater than 1, and it sort of swoops up. So as you can see, it starts out pretty flat and it gets more steeper, or we can say that the slope starts from maybe 0-ish and it goes from 1, 4, 8. So it gets more steeper. So that's one possibility. Another possibility is, think of a parabola going down. So in this parabola, you might think, oh, you're going to start off flat and you're getting more steeper. And you might think, oh, the slope is increasing. Well, you are right in terms of the steepness, but we have to look at the actual slope value. So imagine here you start off slope as 0, and then now you start to get at -1. More steeper means -3. So you look at the values as you progress from left to right. In this case, the values are getting smaller. So, but we want the slope, the actual slope values, the numbers to get bigger. So this graph here does not match increasing in terms of the values. So what else graph can look like? So this one I'm going to erase. So we can actually draw a picture such as, let's have a look. Instead of doing this, let's actually go this way. The other way around, a reflection. So if you look at this graph here, you're starting from left to right. So this is sort of like, let's call this a negative slope. This is also a negative slope, but the number here is -10. And if I'm about to ask you to choose a number for this slope here, it would be probably less than or greater than -10, such as -4, and then it gets sort of less. So if you look at these values, it starts from very negative, not as negative. So these values are actually increases. The slope is increasing from left to right. So we have two curves. Sort of like a parabola-ish going up, and here a parabola-ish feature going down. And for the next one, where the second derivative is negative, when something is negative, something is going down. What is going down? In this case, the slope is going down. So the other example that I erased was very similar to this. So over here, you have a graph. You start off at pretty flat. We'll call it close to 0, and then you start to get negative, more negative, extreme negative, because the tangents are getting more steeper or more negative. In this case, the numbers here are actually decreasing. So this graph here is a representative of a decreasing slope. Another way that you can do this is, another possibility is, for example, this. So imagine like a square root-ish behavior, or maybe a parabola reflected. So if you look at this graph here, we start as very, very steep, like for example, 4. The slope is 4. Over here, the slope would be maybe 1, and over here, the slope is 0. So if you look from left to right, we know that the numbers here are getting less. So in other words, when it comes to second derivative negative, it seems like it's following this sort of shape, meaning sort of like a parabola-ish, or a pieces of a parabola facing down. And for f prime double prime being positive, it seems like it's following pieces of a parabola facing up. So we call this shape here, any part of this graph here, either here, here, or here, this is called concavity, is concave up, whereas this one here to the left here, the parabola is, or the pieces of the parabola are concave down, curving down. So in this next graph, I like for you to sort of figure out, color the regions, if you can imagine, where the graph is curving up versus curving down. So think of a parabola feature. So let's start from left to right. So I'll use a blue pen. So over here, so it seems like this area here, it's curving up to a certain point. We don't know where that point is, so I'm going to put a star beside that point. And after that point, it seems like the rest of the graph is curving down. So in other words, I'm going to put in blue, this area is curving up, and this area is curving down. In other words, the curving up means the second derivative is positive because the slopes are getting bigger. So what that means is, imagine here you have a negative slope, so -5, let's call this tangent here -3, let's call this 0, and let's call this 1. So if you look at the numbers I am sort of like estimating here, they're not accurate, but that we're gauging relative to each other, the numbers here are getting, from here to here, they're getting bigger. Over here, the slope here, let's call it +1, let's call this 0-ish, then it's -1, more steeper, -2, -5. So you look at the progression of numbers here, the slope is getting more negative, or the slope is decreasing. In other words, it's concave down, or the second derivative is negative. And in the future video, we're going to talk about this area here. I might as well just say it right now. So this dot here, this area here, which we'll find out later on, is called the inflection point. It is the point where the graph changes from concave up to concave down, or other way around. In other words, the double prime for this second derivative is neither positive nor negative. It's actually neutral, or we can call it 0 or undefined, but we'll save that for the next video. to find inflection points. So in this slide is the same cubic function from pre-4, but now I actually drew a physical tangent to the graph. So I want you to look at this area over here where the red arrow is. So I want you to just look at the values here. So this is actually the slope of the tangent, the slope of the black tangent line here. So I'm going to take this and start to move, and I want you to observe the values, the actual real slopes. So the previous slide, I just sort of guesstimate. I didn't really do any calculations, but this one, Desmos is actually calculating the actual instantaneous rate of change, or the derivative, or the slope. So let's move this. So let's take this. So as you can see here, the slope is -4. As I move the point to the right, -3, -3.5. So as you can see here, the slope is actually increasing. So it's -3, -2, and it's going to become -1. And eventually it's going to come very flat to 0 soon because I'm going to reach the turning point. And then eventually after the turning point, that's more positive. So let's look at the positive. Positive 2.5, positive 3.6, 3.7, 4, 4.5, 4.5, 4.7, 0.5, 0.51, 0.53, and then almost 0.58, 0.6, 0.61, 0.62, 0.63. Oh, and then all of a sudden, do you see that? It went from 0.63 to 0.62. So that means somewhere around here is my inflection point, because after that inflection point, what happens to the slope? Now it's 0.6, 0.5. Now the slope starts to decrease. So notice how we went from 0.62, and then we have 0.5, and then 0.4. So it starts to decrease. So what I'm trying to say is from here, it's increasing, -0, it's increasing up into 0.63-ish, and then after that, it becomes 6.61, and it starts to decrease. So somewhere here is our inflection point. But regardless of inflection point, look to the left. So we know that it's curving up because the slope is increasing. After the inflection point, we are curving down because all the slopes are decreasing. So let's recap first derivative. So imagine you had a first derivative and you subbed in a value, and if you get a positive number, we know that at that point on the function, the graph is going to go up, so increasing. And if you sub in another a value, and you get a negative number, the slope is negative, that means the graph at that point is going to be going down, decreasing. And if you sub in a and you get a 0, that means it is neither, I'll put here, no increase or decrease. You might call it just flat. Moving on to the second derivative over here, if the second derivative is positive, that means the slope is increasing, or we can call it concave up. So meaning the graph is going to sort of curve up. In other words, it's going to look something like this. It doesn't have to look like an entire parabola. It can have pieces of a parabola, like this piece, or maybe this piece, or maybe this piece. When the second derivative is negative, the graph is going to curve down. I'll put CD, or concave down. It's going to face down. As I said again, it could have pieces of this shape here, maybe this part here, maybe this part here, maybe this part here. It doesn't have to be the entire shape. And the last one here, if the second derivative is 0, it's neutral, that means it is neither curving down or curving up, meaning there is no curving involved. So let's have a look at, we're going to blend in first derivative and second derivative and see what happens, what the graph would look like if something has two conditions. Let's look at the first box here. Well, we know that the first row here, we know that if the second derivative is negative, we're going to have curving down. So I'm going to put here curving down, and curving down. Okay. If we have this one here, it's going to be curving up. So it's going to be curving up, curving up, curving up. However, we're not going to take the entire graph because now we have conditions for the first derivative. So what that means is, well, hold on. Miss, you said that for this box here, over here, this one, I'm doing this one here, you said the slope has to be negative. So we're going to have to take the parabola-ish and then only take things that are going down, decreasing. So I'm going to have to erase a certain part. I'm going to be erasing this part here. Let's make it more nicer looking. So in other words, I'm going to have a function that is curving down like this. Okay. I want to avoid this area because I don't want it to be flat, because if it's flat, then I'm going to sort of deal with the 0 part here. So that's what the graph looks like, what a possible graph looks like. Now let's look at this one here, the very bottom here. So over here, right where the red arrow is. Well, here is a curve, but I only want the positive side. So I'm going to erase the right side of this parabola. So let's erase the right side, and let's try to avoid that flat part of the parabola. So that's what the graph looks like. Let's look at the last column there. We'll skip the middle part here for a while. Let's look at this one here. Let's grab this one over here. Same idea, it's curving up, but I only want the negative part. So I'm going to take the left side over here. I want the positive part because I want the slope to be positive. So I'm just going to erase the certain sections over there. So this one, I want the negative part. This one, I want the positive part. I want to avoid that turning point as best as I can because I don't want anything to like be flat. So what about the middle one here? So what happens? Which part of the parabola are you going to look at if the slope is 0? So you're not going to look at the left side. You're not going to go look at the right side. You're going to look at the very peak. So in other words, this condition here, where this arrow is very specific to a specific point on the parabola or on the curve. I don't want to use the word parabola. Let's call it the curve. It's right there at the peak. In other words, I'm going to use a red pen. This is the spot. So the slope here is 0, but it's still part of a curving down feature. Same thing for here, over here. It's curving up, the graph is curving up, but I want the slope to be 0. Well, where on the parabola feature graph is the slope 0? It's right over here. So this here is a specific point. All right, so let's look at this one over here, the very top here, right over here. Well, what does a graph look like that has no curvature, meaning it doesn't curve up and curve down, but the slope is negative? You've seen it in grade 9 before, your first linear function. It is a line, it's a straight line, but it's going down. In other words, you have a straight line going down, no curvature. That means this one over here, it's going to be going up, positive slope, but there's no curvature. And the last one in the middle, well, what is a line that has no curvature but has no slope? It's a flat line. So here we're going to I'm going to talk a bit about the second derivative test. So we've talked about first derivative test in regards to finding where the slope is 0 and classifying them as a local max or a local min. So whether something faces up or faces down using the first derivative, we had a chart, if you recall. And I'm going to show you an alternative way, a method to classify if something is a max or a local max or local min by using something called the second derivative test. So the question here would be, all right, let's find turning points. Let's classify the local max and local min. Well, we know it's a cubic. Cubic will have most likely in this case 2 turning points. Let's find these turning points here. So we take the first derivative using the power rule. We end up getting x squared minus 2x minus 3. We set the derivative equal to 0, and then we factor, and then we end up getting 2 numbers, which is x equals to 3 and x is negative 1. So how are we going to classify them? Because these could be potential turning points. So if we do the first derivative test, we would actually take an interval chart and we would set the derivative and we would set the negative 1 and 3, and then we would do our positive, negative, and then we figure things out. However, I'm going to show you another method. We're going to use a second derivative. So second derivative, we take the first derivative and then we continue on with the derivative using the power rule. We get 2x minus 2. So what we're going to do next is we're going to take f prime and sub in our critical numbers. So these are our critical numbers where the slope is 0, derivative 0. So we're going to sub in 3 into here. And what do we get? We get 2 bracket 3 minus 2, which equals 2, 4. So what does that mean? So think about a graph where it's concave, second derivative is positive, meaning it's concave up, meaning it looks like this, concave up. But hold on, what does this 3 mean? This 3 means the slope is 0. So where are you on this graph? You're actually over here. So what does that say about this red dot here, which is this 3 here? Well, look at the graph. It's facing up. We know that this red dot here is a local minimum because it's curving up or concave up. Now, if we do the same thing for this one over here, we sub in negative 1 into the second derivative, we end up getting negative 4. The second derivative means, if its second derivative is negative, it is curving down, meaning the graph is going to curve down. And I know for a fact right now that because it's curving down, and this is my red dot here, because the slope is 0 on this area, we know this is a local maximum. So this is our second derivative test. It's an option. You don't have to do, if you don't like the first derivative test in terms of interval chart, you can actually use the second derivative. Now, it really depends how complicated the function is. If the function is relatively simple to keep on going with the derivative, then you could use second derivative. If the function is more complicated and it actually takes a lot more work to get to the second derivative, then second derivative tests would not be the ideal. It really depends on the function. So in this graph, I'm going to ask you, well, where is the second derivative positive or negative? Well, in other words, concave up and concave down. So over here, we can see that this part here, this area here that I'm scribbling, is curving down up until a certain point, and after that, I'll use green. Over here is going to be curving up. So this is curving up, and this is curving down. In other words, second derivative is negative in the red, and over here, the second derivative is, f prime is positive. Very similar here, look at the beginning of the graph. Over here, the graph is curving down, so put here concave down, curving down, or the second derivative is negative, and over here, this green area is curving up, or the second derivative is positive. And see if later on in the next video, the transition between red and green is called the inflection point. So over here, another graph here. Over here, I can tell you right now, this seems like it's curving up until a certain point, which we don't know where it is, but eventually it's going to be curving down. So curve down, curve down. I'm going to rely on symmetry here. And over here, it's curving up, swooping up. So the green area is curving up, CU. And then this second derivative is positive, second derivative is positive. And over here, this red area here is curving down. Our second derivative is negative, and this might as well just go to the next concept here. This area, where the transition from green to red or red to green is called the inflection point, and the second derivative is neither positive or negative. It's going to be neutral. So when I say neutral, it's going to be 0 or undefined.